We'll be discussing about image annotation, what is image annotation, and what are different ways to approach to this problem. Earlier in computer vision, given an image, the aim was to detect an object present in the image. For example, in this image, the aim was only to predict horse. But now there's a slight change in problem definition. Now automatic image annotation is a computer vision task which aims at assigning a set of appropriate labels to a new image. The aim is to eventually bridge the semantic gap of visual and textual representations. That is, given an image, we want to annotate all the things present in the image. For example, in this image, we want to annotate fountain, tree, building, road, etc. There are several applications to image annotation problem. For example, in image retrieval systems, we want an image to be retrieved given the characteristics of an image. In robot navigation, we want a robot to navigate understanding the view in which he is navigating. Also, in visual assistant systems, we want the understanding of image to be given to visually impaired person so that he can differentiate between an obstacle and his target. Earlier, several approaches were proposed ranging from SVMs to decision trees to solve the problem. But in 2008, Makadia, Pavlovic, and Kumar presented a new baselining to solve the image annotation problem. JEC. JEC utilizes low-level image features and a simple combination of basic distances to find nearest neighbors of a given image. Each feature contributes equally towards the image distance, so appropriate scaling is required before we add them together. The scale distance is referred to as joint equal contribution or JEC. It then uses a greedy label transfer algorithm to assign labels to a new image. JEC utilizes individual label frequencies and label co-occurrence frequency to predict the labels of a new image. Given a new image, let I1 is the closest neighbor of the image. Then we rank all the keywords present in I1 according to their frequency in the training set. Of all the keywords present in I1, we transfer n highest ranking keywords to the test image I. Now, we rank all the keywords present in second nearest neighbor I2 through IK using two factors. First, the co-occurrence of them in the training set, and second, using the local frequency of the present label. Now, we transfer the highest ranking remaining keywords to the image. In 2009, Matthew et al. Proposed discriminative metric learning in nearest neighbor models for image auto-annotation task. TagProp. TagProp is a discriminatively trained nearest neighbor model. It predicts tags by taking a weighted combination of the tag present or absent among the neighbors. First, the weights of neighbors are either determined based on the neighbor rank or its distance. TagProp also allows integration of metric learning by directly maximizing the log likelihood of tag predictions in the training set. It uses word-specific sigmoidal modulation of the weighted neighbor tag predictions to boost the recall of rare words. Thus, it somewhat approaches the problem of rare labels and class imbalance. For TagProp, a combination of local and global features are used. The local features include SIFT and hue descriptors, and the global features comprises of histograms in different color spaces like RGB, HSV, and lab. The TagProp model consists of four different parts. Part 1 encodes associations between image level labels and global visual features. The Part 2 models associations between regional level labels and local visual features. Part 3 captures the inter-label correlations dependent on image features. And Part 4 measures the coherence between image level labels and region level labels. In 2012, Yashasvi Verma and C.V. Jawahar proposed a two-step variant of classical KNN algorithm. The new algorithm was explicitly proposed to handle the issues of class imbalance and weak labeling. There were two steps in the proposed algorithm. In first step, the identification of semantic neighbors corresponding to all the labels are done, and in second step, these neighbors are used for label prediction for a given image. The first step of 2pKNN uses image to label similarities, while the second step uses image to image similarities. Given a test image T, for every label L in the dictionary, we select top k nearest images from train image set to build a train subset for the image. In phase 2, with this subset, we run the KNN to find the labels for the image. This selection of train subset ensures that even the least frequent labels are present at least k times in the train subset, thus giving them comparable weightage while testing. We can clearly see in the given examples that river, which is a rare image, is still present in the tags predicted by 2pKNN algorithm. Now, let us move to the experiments that are done to tell which algorithm performs better in which conditions and what are the advantages and disadvantages of the above discussed three algorithms. So, to do all the experiments, we are using the most popular image annotation dataset, Coral. In Coral, there are 5,000 images which are divided into 4,500 train images and 499 test images. There are 260 labels in the dictionary. Now, for evaluating the features of the images, we are using 15 distinctive descriptors, which include SIFT and hue-based descriptors. And to cover the overall characteristics of the image, we are using histogram and gist-based descriptors. As it is very clear that nearest neighbor based approaches highly depend on what kind of distance measures are used. So, following the earlier research work, we have used different distance measures for all the 15 distinct descriptors. L1 measure is used for colored histograms, L2 for gist, and chi-square for SIFT and hue descriptors. We also have 258 dimensional correlated feature vector, which is hereby referred as feed2, for which distances are measured using Euclidean distance. Now we have used evaluation methodology which was used earlier by the papers to compare them. That is precision, recall, F1 score and N plus. N plus is the number of labels that are assigned correctly to at least one image, that is, which is having a positive recall value. So we are comparing three different methods and their variants to see what algorithm performs better. For JEC, there is just one variant which is referred to as V1. For TagProp, there are four variants including single distance and machine learning. And for 2pKNN, there are two variants, one simple and one includes machine learning. Similarly, we have different evaluation strategies. These experiments are basically designed to compare individual algorithms. In first algorithm, we will see just the performance of JEC. In second experiment, we will see performances of all the different variants of TagProp. In third experiment, we will see performances of all the variants of 2pKNN, and similarly till the experiment 8. The The first experiment that is done is to compare what the results that we get with the previously defined results by the authors. So we have used similar settings and tried to achieve their results. As we can clearly see that we are able to achieve the similar results, there is a little variation in the results, but that is because of lack of experimentation to decide the parameters. Now we have also shown results for feed2, that is a correlated vector, and we can clearly see that instead of using a long vector, if we use proper projections of the vector, we can get better results. So feature 2 is performing better than feature 1 in all the cases. Experiment 2 is understanding the role of validation set while doing the k nearest neighbors in the nearest neighbor settings. Validation data is used essentially to tune the parameters of a classifier and to avoid overfitting while training. Clearly, in nearest neighbor based approaches, there's a high requirement to tune the parameters so as to get the optimum value from an algorithm. Since JC has no parameters in it, the validation we have not used validation data for that. For TagProp, there are four different variants, out of which in this experiment we are showing the use of validation data for simple single distance TagProp, and for 2pKNN there are two parameters, that is K and W. As the value of K is mentioned explicitly in paper as 4, we have used the validation set to determine the optimum value for W. While using the validation data, one question that comes to our mind is what should be the ratio of training data versus the validation data? In these two plots, we have shown in these two plots, we have shown the role of size of validation data in TagProp and 2pKNN. So in 2pKNN, since we can see that the peak values are at validation data size 2500. So for 2pKNN for finding out the value of W, we have used a validation data of size 2500. Similarly, for TagProp, we have used the validation data of 2000. In this graph, it is clear that there's a trade-off between recall and precision at a value of 200. So we are using 200 nearest neighbors for TagProp algorithm. Similarly, for 2pkn algorithm, we can clearly see the optimum value of W is coming out to be 14. So we have used the value of 14 for doing the further experiments for 2pkn. In this experiment, instead of average performance, we are measuring performances for individual labels. For this experiment, we have sorted the label based on their frequencies in train set. It is clear from this plot that there is a high variation in frequencies of the labels. The most frequent label is present 1004 times in the train dataset, while the least frequent labels are present just for one images. This shows high variance in the frequency of labels present in the training set, which is the problem of class imbalance. For the further experiments, we have arranged the labels in the order of their frequencies in the trained dataset. Now we can clearly see this is the plot for the performance measures for the JEC dataset, JEC algorithm. This is the precision, recall, and F1 score. It is clear from the figure that the least frequent labels have almost zero precision, zero recall, and zero F1 score for JEC. But in case of 2pKNN, we can clearly see But in case of 2pKNN, we can clearly see that even the least frequent labels have some precision and recall values. This shows that 2pKNN somewhat approaches the problem of class imbalance. In experiment 4, we are analyzing the performances of above three algorithms qualitatively. That is, we have taken out test images for which JEC is performing better than TagProp and 2pKNN. In this figure, it is clear. Let's say the example of image 2. The ground truth label contains sky, jet, plane, and smoke. The JEC algorithm is able to predict all four labels correctly, but the other two algorithms are failing badly for this picture. Similarly, in this image, we have shown the images for which TagProp is performing better than JEC and 2pKNN. Clearly, for this setting, for this image, the ground truth annotations are bridge, building, and arc, for which TagProp is predicting bridge correctly. But neither JEC nor 2pKNN is even able to predict the bridge. Similar to the above cases, in this image we are showing the images for which 2pKN is performing better than TagProp and JEC. Let's take the example of fifth image. In this image, the ground truth annotations contain smoke, train, locomotive, and railroad. In the 2pKNN is predicting all the four labels correctly, plus it is predicting the weakly labeled label sky, which is present in the image, but due to human errors was not annotated in the ground truth. For experiment 4, we are analyzing the issue of class imbalance. As discussed earlier, due to the significant varying of frequencies of labels in the training images, there is a huge difference between the performances of the most frequent and the least frequent labels. Thus, it becomes important for an image annotation algorithm to maintain some balance in performances of these labels. Here, for analyzing the performances of frequent versus infrequent labels, we have created two bins of 50% labels. First bin contains 130 of most frequent labels and second bin contains 130 of the least frequent labels. It is clear from the graph that cumulative frequencies of these bins vary significantly. The most frequent labels has a cumulative frequency of around 14,000 while the least frequent labels are not present even in the 20,000 images. Now, let us analyze the performances of all different methods under this setting. In this image, the blue line shows precision, green line shows recall, and the brown line shows F1 score. Similarly, the red line shows N plus. It is clear from the image that for JEC algorithm, performances of the labels which are frequent is much better than performances for the labels which are infrequent. Similarly, we are able to predict near about 100 labels out of 130 correctly for frequent labels, but we are not even able to predict 30 infrequent labels correctly for JEC. Similarly, for TagProp, we can clearly see that the performances of labels which are frequent is significantly high than the performances of labels which are infrequent. This shows precision value for the for all four variants of TagProp. This is recall for all four variants of TagProp. Similarly, this is F1 score and this is N plus. In this image, let us analyze how 2pKNN performs for frequent and infrequent labels. Given infrequent labels, it is clear from this graph that the recall of infrequent labels for 2pKNN is much higher than any other algorithm. For 2pKNN, the recall of infrequent labels is more than the recall of frequent labels. Thus, it makes a clear understanding that 2pKNN is able to predict even the weak labels. Also from this image, this is the N plus image for 2pKNN, it is clear that we are able to predict more than 60 infrequent labels correctly out of 130 infrequent labels. In this experiment, we will analyze the problem of incomplete labeling. That is, due to human error, tags which are very common are not annotated in the images. For example, given an image of a room, a human annotator tend to forget to label wall because it is very explicit for us. So for this setting, we have removed 40% of the labels from the ground truth data. This graph shows the frequencies of labels before and after removing the labels. Before removing the labels, the most frequent label is having the frequency of 1004, while after removing the frequency goes significantly down. In this setting, let us compare how the algorithms perform. So the red bar is for JEC, the pink bar is for TagProp SD. So it is clear that if while after removing the labels, precision for JEC significantly goes down. Earlier, the precision for JEC was 27 and now we can see that the precision goes down to 21.8. Clearly, precision for other algorithm also goes down. But even in the case of weak labeling, where the most common labels are not present in the images, it is very evident from the graph that 2pKNN is still performing better than the other algorithms. This clearly says that 2pKNN approaches the problem of weak labeling very well. Similarly, we can see that also the recall of 2pKNN is better than all the approaches. Recall of TagProp is better than JEC, but recall of 2pKNN is better than all the variants of TagProp as well as JEC. This table gives a bird eye view about the performances of JEC, TagProp and 2pkn in the setting where 40% of the labels are randomly removed from the ground truth of training data. We can clearly see that 2pkn the results are extremely better than the other two methods. For 2pkn the n plus is 160, which is significantly high from the other two methods. In this experiment, we will compare how the individual methods are performing for frequent labels. Thus, we've only kept 75% of the most frequent labels in the training as well as test annotations. After removing the labels, all those images that have no labels in the ground truth are removed from training and trend subset. This experiment compares performances of all the methods and their variant for frequent labels. This figure shows the bar plots of all the methods and their variants, how they are performing in case of such setting. We can clearly see that for the frequent labels, precision for JEC, TagProp and 2pkn increased than the precision of overall. So for the most frequent 75% of labels, precision for JEC increased from 0.27 to 0.29. Similarly for 2pkn and TagProp. But still we can clearly see from this figure that TagProp machine learning is performing better than JEC. But 2pkn plus 2pkn machine learning is performing better than TagProp and JEC for all the settings. Similarly, in the recall graph, we can see that 2pkn machine learning is performing better than TagProp and TagProp is performing better than JEC. This is the n plus graph for the above setting. We can clearly see that even in this graph, the trend is followed. JEC is performing at 120 while TagProp is having better performance and 2pkn even the performance is increased. Table 4 shows a bird eye view about all the methods and their variants and their performances on top 75% of the most frequent labels. We can clearly see that the performance of JEC precision is 25 and the performance of TagProp the precision improved to 31, 34 and for 2pkn precision improved to 45. So for the normal case, 2pkn precision was 40, but for the case of most frequent label, precision improved to 45. Similar is the case with recall. Recall increases to 46. Similar to experiment 3, as we've considered only the frequent labels, in this experiment we will consider only the rare labels. So for this experiment, we have shrinked both training and test dataset by keeping only top 25% of the less frequent labels. Thus, after removing the labels, all those images that have no labels in the ground truth are removed. This experiment compares the performances of all the methods and their variants for the least frequent labels. The precision graph for this setting shows us that there's a significant decrease in performances for all the methods. While JEC was performing at the precision of 27% for normal case, here for infrequent labels, JEC's precision goes down to 0.10. Similarly in TagProp, the precision grows down to nearly 0.13. But 2pkn is still performing better with a precision of 0.22. The precision from 2pkn decreased from 0.39 to 0.22, but still the precision is better than the other two methods. Similarly, the recall. We can clearly see that recall of 2pkn is better than the recall of TagProp and is better than the recall of JEC. The N plus score also follows the same trend with JEC performing a little less than TagProp, which performs a little more less than 2pkn. Table 5 shows bird eye view about the performances comparison among different image annotation methods after shrinking the training and test dataset by keeping only the top 25% of least frequent labels. We can clearly see that precision, recall, all significantly decreased for all the methods. But for 2pKNN, the performance is still comparable to JEC, TagProp original settings. In this section, we've tried to approach to the same problem with a different manner. We've tried to use one versus rest SVMs to approach to the problem. Let us consider a training set T containing T images in total, where image I1 is having label set of L1 in the ground truth. As we all know that in typical annotation task, there is a predefined set called vocabulary of labels. Let that set be y1 to yl. Now we will try to approach to a problem training LSVMs, that is one SVM per label. So the SVMs will range from S1 to SL. For any new unannotated test image, we will try to pass that image features to all the SVMs and try to get scores for them. For every testing image, we pass into the pre-trained set of L classifiers. The classifier score per label per test image is taken as output. For every test image, top 5 labels are assigned to it as the output. Figure This table shows clearly that one versus rest SVM, the results are comparable to the latest state of the art method, that is 2pKNN. The N plus score is better than 2pKNN, F1 score is better than 2pKNN, and our recall is better than 2pKNN. The precision, there is a slight decrease in precision as compared to 2pKNN. But still, in case of 2pKNN, we are at the time of testing, we are comparing every test image with a predefined subset of train images. But uh, in case of SVMs, we are just passing the image to a SVM classifier and getting the output, which is slightly computationally efficient and decreases the training time. This is the snippet of code that is used for training of SVMs. Here we are training a total of L. If the number of labels are L, then we are training a total of L SVMs, and given any test image, we are passing the test image features to each of the SVM to get the output. Now we are using this SVM output to choose top 5 outputs, and we assign top 5 scores to the test image and calculate the performance from it. With this experiment, we have clearly shown that even a simple conventional one versus rest SVM can perform similar to the with the state of the art methods. So the total understanding of this whole experiment includes the nearest neighbor settings, the problems and the experiments that needs to be done while checking any algorithm, while comparing the algorithm with previous work and while designing the algorithm. Here we've also learned about matrix learning, which is treating different weights treating different features differently. So in matrix learning 2pKNN, we have seen that some out of the 15 features that we've discussed earlier, some features were given weights as 1, while some features were given weight as low as 0.01. Thus we analyzed that different features contributes differently to the classification task. Some features are important while some features are lesser important than the other features. Thank you.